phase fix and the depolarizing channel and all. Now let's come to some programming sessions. So somebody was asking me beginning of this class, what are the packages you need to install? So you just need to install the three packages individually run. One is the Qiskit package. So you do the pip install Qiskit in your Python environment. If you directly do the pip install Qiskit, so it will by default it will download the Qiskit 2.0, the 2.0.1. So basically it will be the version 2.0.1 presently. Or if you just write this command that some of the previous packages are already there, so you don't directly install this. You do qt install qiskit equals to say some version 1.0.0. Suppose this way also you can install the qiskit for your experimentation. Once you do that, you need another package because you might need IBM runtime such as the estimator and the sampler primitive for getting your results, measurement results, getting the histogram and all. So this is the package for that. Various like running your circuit on the IBM machine using the IBM primitives and all. For that, you need to install the Qiskit IBM runtime. Okay, so pip install that. Once you do that, then you might need something and that is called the this particular package called the Qiskit visualization. So if you do not install this, still you can run a circuit here. Okay, say for example, let me show you an example how it works. Okay, so suppose I do call certain libraries. Okay, um, say I take the quantum circuit transpile, the parameter vector, the generic backend. So if you are using the Qiskit 2.0, you don't need to install the Qiskit ER packages for that. Instead, you can simply call the generic backend to run your experiment on the simulator. So this is for the especially for the Qiskit 2.0. If you do not have Qiskit 2.0, you can install the Qiskit ER for Qiskit 1.0 or Qiskit 0.0 versions, and accordingly you can get the result in the estimate side. Okay, so let me give you one example maybe for the participants that might be helpful. Okay, yeah, theory is sometimes boring, so some of the people I think left, and also I'm so sorry I'm taking a long classes like 3 hours, and thanks at least 260 participants I can see. Okay, so that's it. Let's run this and let's do a quantum circuit. Okay, suppose this is not a Qiskit session, so I won't go much. So suppose um, this is a quantum circuit of say 2 qubits, and I want to draw the circuit. You see dot draw. Okay, so you see it has taken 2 qubit q0 and q1. Okay, just by defining Q is equals to quantum circuit 2, between two quantum registers. Okay, if I assign one classical register or two classical register, also you can see that there are two quantum register and two classical register as well. Okay, now suppose you apply Hadamard gate in the first qubit, QC dot H in the first qubit. So first qubit always start with the 0 position. Okay, and you draw this. So you can see this Hadamard gate applied on the first qubit, and then you create an entanglement between the first qubit and the second qubit between 0 and 1. So you can see the CX gate is applied between the qubit 0 and the qubit 1. Now, if you can do that, so basically, without installing this package visualization, okay, you can draw after this, but with the visualization, you can do a bit more colorful plots and many other things. So by the command MPL, if you run this, so it will look like this. And then you can do like the measurement if you want to do QC.measure all and other comments are there. to do this. So like you want to execute the circuit on the back end, like the generic backend, for example. Say I call this one the sampler. Num qubit is not defined. Suppose say number of qubit equals to 2. And then if you run this, then I can use this sampler for the result. So let me write the code for this. So so let me first do the QC dot measure all here, and I can draw the circuit QC dot draw again with the NPL comment. So you can see I have done the measurement in the first qubit as well as the second qubit, and the measured result are stored in the classical registers, two classical registers that I have taken, right? And if you run it on the simulator with this particular experiments, you can get the histogram for this particular result, right? So so I have called the sampler, right? And then let me retrieve the values. So can you please paste the code here for hands-on session? Yeah, sure, why not? So for the installation, let me give you the packages here. You can directly try include it. I included both the yeah, please you can try the code with me as well. If you stuck somewhere, you can ask me so I can decode online. Once you do that, I call this libraries for the code, and then I define the quantum circuit like this, some bell stick circuit. Yeah. And I printed this one, and just allow me some time. So let me try this one. Let's take one. So suppose I want to run this circuit for 1024 sorts. Let me try this. And job equals to backend dot run. I don't know whether it will work or not. Just let me try this. And suppose so my circuit name is QC, right? QC transparent. Backend is not defined. Backend, take backend. So sample confirm, maybe I can try. There are some errors coming, okay? So let me try this code then. Yeah. So so you can see that what I have done is I have called the generic backend here. I have defined a Bell circuit with two quantum registers with two classical register. I applied the Hadamard gate in the first qubit, applied the CX gate in the between 0 and first qubit, same as the earlier circuit. I am measuring on the 0 and 1, 0 and 1. Then I am displaying the circuit. So this is the displayed circuit. So within draw, you can do MPL. So instead of this command, I can do MPL. So It's maybe requiring another cell for this. Yeah. And then basically I called the generic backend the same thing. So you just need to do this thing. So the 00 is coming 502 times and 11 state is coming 522 times. So roughly because I simulated the experiment for 1024 times, right? And there is no other state. So 01 state is not there and 10 state is not there. Only the entangled state 00 and 11 appeared in this picture. So this is basically the belt state. And okay, let me try this. This is the histogram you can see. Okay. So if you increase the number of sorts from 1024 say, to 100, say, and you can see the experiment is 50-50. Okay. But this is not the case that you will be getting 50-50. That may be a bit less or more because of the impact of noise. So less number of gates and less number of quantum sorts, less uncertainty. So more if you do 10,000 times instead, and then you can see that this is not 5,000, 5,000. Okay, so there is something like this. But still you are running the experiment on the simulator. If you try it on the actual IBM hardware, you'll see this figure is changing. These two figures are changing. Okay, these two plots are changing. Line 4 of that cell can cause fake backend. Okay, let's try this code. I'm sharing you a new code for now. Um, oh, I cannot paste all the lines here. That is the problem. This Google, this meeting chat is not allowing me. Okay, don't worry. I'll be sharing the things. But at least, okay, let me try by line. If I can give you. So remove the, okay. So instead of the last line of the thing, you can directly give this, or you can print the fig. So it will show you the plot. Okay, and now let me, so this is like how a quantum circuit works in Qiskit and the impact of the measurement noise. Okay. Now let's come back with some more things. Okay, so let's first do the linear regression thing. So as I promised that I'll be doing some statistical inference, and I'll be sharing the code and some few lines of the codes are described there. But in the notes I shared how the statistical inference theories work. So some coding on those things. So first the least square problem. So what so let's take a synthetic data point, something like we have taken the random data points, 42 random data points, and I define a random variable x, which is an NP array, 1, 2, 3, 4, 5 sorted array up to 1 to 10. I take a true slope like a linear equation for that mx plus c, where m equals to 2.5 and c equals to 5. And my equation is basically true equation is basically mx plus c, like the true slope into x plus the true intercept, right? This is my equation. And I can generate the noisy data with some true data plus some random noise added to the signal true value, right? So if I generate a data something like that, so there is some error coming NP. So I have to define what is NP. So import numpy as NP. And this is the noisy data. So let me import mat.lead.pyplot as BLT. So I can plot this noisy data. So this is the noisy data points. If you want to see like the star, star point maybe. Yeah, this is your noisy data. It should supposed to be the if you draw this thing like plt dot plot of the true data points, and the true data is y2, and you are marking them at star. So so what is there? Plt, okay, plt dot plot. So you see all the blue points here. Blue points are the true points, like that is following the straight line equation. Whereas from the real data set, what you get are this orange plus point, right, which are not true. Now you have to find an estimator that will give a closer line to this, basically the actual points, because you have an observation. You have to train a line which should follow this blue curve, because blue curve is not given to you. You have only the observed signal, and from that you have to estimate something like two parameters, the intercept and the slope, right? And that estimation we have to do, and then we can see whether that is matching to the actual line blue or not. Okay. So if I remove these things, like it can be a straight line probably. Yeah. So this line we have to estimate from the algorithm called the least square estimate. Okay. So for that, the least square thing we have learned last week from the matrix computation. So every time, of course, there will be some error, and that error we have to minimize from the equation. And basically, what we'll do, we'll create a matrix A, and from that we will do the pseudo inversion, and from there we will, or you can directly call the least square fitting from the NumPy library, or you can design your own. So least square formulation, that is basically your a dagger, so a star, whole inverse, right? Whole inverse, and this side probably star. I have to check the formula. So there are two versions for this, times the observation vector y noisy. So that will give you the estimate, right, of x. That you can do. Estimate x you can do. So this is the formula I'm writing. So this is what it is done. Right? This is the formula. If you do that, and if you call this library least square fitting, so they will give you the same result. And if you run these things, so basically we get an estimate regression line, this red one, where the true line is the blue green dot one. But previously it was the blue. Now I have drawn it with the green line, right? And from the least square estimation, we have estimated a line red. Of course, there is some error between the true and the estimated result. So let me share the code for this in the chat so that you can try. So similarly, you can calculate there are like type 1 error calculation, type 2 error calculation. Say for example, if somebody is tested with certain parameters, we have to decide whether he or she is infected with COVID or not, or a particular disease or not. So this kind of decision making thing. So there is like let me show one example of such cases, and then I'll share the code with you. So maybe sometimes there are library mismatch, stat and all. I have to call from certain libraries. So let me find some libraries for this. Maybe this is from this one. False negative. This is a false negative result, and then I see issue short. What is this plot? I have to plot this right now. Yes, this one. So, okay, I haven't covered what is null distribution. All these things I have given in the notes. So there are various techniques like the Neyman-Pearson lemma, the Bayesian risk phenomena, and all. But in general, you decide a hypothesis that if something happens, so you take that hypothesis accepted or you rejected it. So corresponding to that particular statement. So from this plot, actually, there are certain things like the critical region is this red line, and how much power is distributed within this critical region, and based on that, you decide whether to consider these null hypothesis or the alternative hypothesis. In this particular case, we have seen that it is a basically false negative case. So basically that is a type 1 error basically. So okay, so this part might be like taken side by side, uh, but let me come to the point of this. Okay, this is run in the air simulator. Air simulator might have some issue, right? So this is the generic backend I have to call. Mm, so let me try this. Just give me 1 minute. So if you are using the like Qiskit AR, let me try if I have the Qiskit AR thing. Qiskit AR is not installed here. This error might happen if you are using this Qiskit 2.0. And for that, you need to install this pip install Qiskit AR, especially if it is a old version. And then basically, if you complete this installation, let me try the same code again. So let me call this libraries. So yeah, I'll be sharing the Python file, don't worry. Just let me draw a quantum circuit and try to do at least one error correction code, that is the repetition code I'll try today and close the session. Ritojit will cover a lot on these mitigation techniques tomorrow based on the theory I taught. Maybe some practical other aspects also he will introduce tomorrow. So yeah, so let's take a circuit like this. So let's take a single qubit quantum circuit, just apply the Hadamard gate and run for the 1,000 times, right? So if you apply the H Hadamard on the 0, so it does the superposition of 0 and 1, right? And if you do the superposition of 0 and 1, so definitely you expect that it will be 50%, and after out of thousands or they should be 500, 500, something like this, right? So let me give you the code also, those who are trying parallelly. Plot the histogram gradient. The last line, probably there is some issue. Yeah. So let's run this code. You see the probability is not exactly 50%. So 0.505 and 0.495. That means there is some uncertainty in the generation of the state 0 and 1. And how it is coming, why it is coming, so and how to mitigate this particular error thing. So there are ways like the quantum error correction and error mitigation. So it will show tomorrow. Okay, let's do a basic bit flip noise that just we learned bit flip noise. Okay, good for that. So so these are some important libraries, and I assume that the probability that the bit flip happens is 10%, and I assume a noise model. Okay, that is a bit flip error noise model I considered. So what I did is I have taken a single qubit quantum gate and a single quantum like the classical register, and then I measure on the 0, 0 state, right? And then apply the X gate on the first qubit and measure it again. I repeat the experiment for 1,000 times and let me see how the things comes, right? So zero state is again like before applying the poly gates like with the error channel. You say the zero is highly likely, right? Because it started with a quantum state that is in the state zero, right? The generation of the state is zero. So at the initial start of the class, I told even if you think that your get zero state is a perfect state, that is not the case because some hardware is generating that state, and you can see like out of 1,000 times what you thought it is zero, but it is only 898 times zero in this particular case, and 1,000 and 102 get zero state still appear due to the generation of the qubit itself. Now you apply the bit flip channel here, okay? And if you apply the bit flip channel here using the Krauss operator settings that we have seen in the theory, so your zero is changed to one, right? So then get one state, if you repeat the experiment for 1,000 times, and it is supposed to be 1,000, right? But still at the measurement, because of the measurement error, there are some zero is initiated here. So of course it is 0 to 1 is happening, but this small zero probability and small zero 1 probability and small zero probabilities, these are coming due to the measurement noise, and this is due to the generation noise. Okay. So I'll share the code. Don't worry. Just let me just complete this part, and uh, so let's try this one. Majority voting based error mitigation techniques. Okay. Um, So let's do this thing. Yeah, he will do the zero noise extrapolation and other things. I mean, not though detail, but yeah, something. Suppose you generate some ideal state like the P0 state with a very high probability, 100%, like probability of the state zero, right? And because of the generation of the noise, you have a noisy state with, and the probability of zero is like now reduced to some values, right? And there is a chance of generating the values of the probabilities of the state one. So this is given by red. Now you have a error mitigation technique that is based on something called the what we say the repetition code using the majority voting. Okay. So what is that? I haven't covered the theory, but let me write a few sentences maybe to the clarification part. So, so while full quantum error correction is complex, we can illustrate a very basic quantum error mitigation strategy using repetition codes and the majority voting. So this is a statistical approach to combat noise. So you repeated the number of measurements, okay, and you try to minimize the effect of the error by averaging. So to protect a logical qubit, we encode it into multiple physical qubits. For example, to protect get zero, we encode it into 0, 0, 0. Okay. And if one qubit flips, we can still recover the original signal by majority voting. That means you instead of creating 1, 0, you create many such zeros, 0, 0, 0, triple 0. And maybe one of that particular zero can be one, but you are trusting the overall result, cumulative result for all three zero. If the majority of the zero is still zero, so you consider zero. If some of the zero becomes one and the majority becomes one, you consider it one. So this is one repetition code. Instead of single qubit, you create a multiple qubit, and then basically you try to mitigate the error that some of the quantum state that is still in zero by majority, I can vote that particular state as a true state, and I can minimize the error a bit. If it is not a fully error mitigation techniques. It's an example how it is done, okay, by repetition code. Okay, and then let's do a bit more on this direction that can I improve the result bit? Yes, you can improve the result bit. So in this particular case, um, so I have taken the bit flip error, okay, as the error model, and then basically simulated the experiment. There is a whole detailed code for that. And then I applied the repetition code with certain more basically by increasing the number of repetition code from 3 to 6, right? And let me check the answer is improved from here to the result that I am getting. The probability is still less than 80%, right? Something like that. The probability of 0, right? So if I increase the number of repetition code, can it can this result be better? So you can see right now this was your noisy state, and now it is almost better than 90% of the state 0, right? So this is how this error correcting codes work. I mean, I haven't told the theory, and that because that is not part of this QT-03, but just a notion that how probability theory works in quantum measurement, qubit generation, as a whole, to appreciate that this quantum theory requires the knowledge of probability and uh, statistical parameter estimation and other things. So with this, I conclude these sessions here today, and I'm open to take questions. So I took a stressed class today. I'm so sorry to make you wait for this long time in on Saturday, and thanks a lot because you spent a lot of time here today. So you will tomorrow you will see a lot of such practical things with the circuit design, different types of errors, how to handle errors in the practical circuits. So Dr. Ritojit is an expert in this area, error mitigation techniques. I am very poor in this area. I just try to understand how this works and how I understand the theory. I try to share with you all, and I'll share the entire code for the Python for yesterday that I showed you, today that I am covering. Both the codes I'll be sharing, the theory, the notes, and all I'll be sharing. But to appreciate that how actually it is working and all the practical aspects. So Dr. Ritojit is an expert in this area, error mitigation technique, and I hope you will enjoy his session. He's my colleague at IBM, and I really am happy that he is taking the practical session of the theory thing that I covered. Thanks a lot.
Hello. Am I audible, sir?
Yeah, yeah, please.
Ah. So,
Sorry, I just
thank you so
stopped
much, sir.
there 7 minutes back because I thought 3 hours is a very stressed for everyone. So I stopped it
No
here
issue.
because it's overall it's completed, I think. Yeah.
Yes, yes. No issue, sir. Sir, there are some questions in the chat box, sir. Uh,
Yes.
so,
So many of the questions are related to the codes that I just showed the example. I'll be sharing the code. So those will be cleared. There is one question. Could you please share the error mitigation code? Yeah, Ritojit, Dr. Ritojit will take a lot more like detailed session on this. I'll share the code. Then I read the phase flip is difficult to correct than bit flip. Yes, correct. Can you explain? So again, please repeat this question to Dr. Ritojit. And yeah, so tomorrow he'll because he's working on the mitigation and error correction. Okay. I am in the simulation, quantum simulation side. Definitely I have some answer, but he is better to answer this question. Is there a threshold value? So as such to the bit flip noise above which it causes the probability to flip. Yes, there are some theoretical bound for that. We do not know the exact threshold, but there is bound. Um, yeah, thanks a lot. I mean, feel free to ask questions. So they are asking some questions to you, sir. So will this chat session will be there or not? I don't know. Like you can answer better. You can share.
definitely it is for the session by session. So, definitely it won't be there. Uh, Mostly it will not be there. It is just for the session to communicate your questions or any query you have.
Right.
So,
So
anyway, I think, yes, sir,
yes,
yes,
sir.
sir.
So if possible, because this is experiment like the QT-1, 2, 3 that you are doing already, this is an excellent way how you are organizing things. But if possible, that in the next QT to add some chat like way how people can interact more with the instructor. I mean, I don't know the solution. Just this is an issue. That's why if there is like because they want to keep the chat to understand how the question and answer for their the classes that they will offer in their institutions, that these kind of questions can come. So I don't know, like this somehow it can be done, or I don't know, like you can discuss maybe.
Sir, definitely we will look into it. We are also eager to basically create that environment, but due to that software limitation, we are unable to do so for the time being. But
Yeah,
definitely in the near future, we will work it out.
right.
And so, how
Yes, sir.
can we get
Yeah,
this?
thanks a lot. Like there is one solution from NPTEL. Some of my colleagues and I took some courses. They do some sort of like forum, like one class, like doubt clearing or anything from the.
Mhm.
I don't know whether that is possible or not. For the time being, it might not be possible, but maybe a future solution we can consider.
Sure, sir. Definitely, we will try to look into this. That actually, we are also working on that one, how to basically make the session more interactive than this chat one only. But
Mhm.
the way means once we allow the live interaction, it will be difficult to basically synchronize all the things.
I
So that's
understand.
why. Uh,
I agree. I agree.
so
Yeah.
so anyway, I think. Non-programming. Yes, definitely. Some basic knowledge of programming is required. I know that difficulty you may be facing, but most of the portion, the last portion, except the last portion, most of the session was about we can say mathematical background. So I think you will follow once you will revisit the topic. You can go through the YouTube link and you can just go through the videos again and again. Definitely, you will get the idea. So for the first time, it will be difficult if you are very
Yeah, and
beginner to the
also,
programming.
sir, probably if I follow correctly, QT-03 course, beginning there are some programming sessions, right, in the first two, three
Exactly. Yes,
modules.
sir. Yes, sir.
Yes, so I hope if you repeat those things and if you consult with the instructor who taught it, that will be very much beneficial too. I thought the basic programming is taught or known. That's why because if I want to teach the programming itself, it is another two, three modules. So better you who already taught. I hope it is explained very well. Please have a look on
Yes,
those
yes,
topics.
yes. Really, sir has really taught well that programming.
Yeah, I
I have
hope so.
also
Yeah,
followed those lectures, sir.
yeah, please. Yeah,
Anyway, thank you so much, sir, for your insightful session. The session was very much informative. And thank you all the participants for your interactive involvement in the session. And some of you have also solved the problems given by the sir. So that was also a good thing. So thank you for your active attention to the session, because on online session it will be it is difficult to
right.
have your attention most of the time. So anyway, I am seeing the active participation, that is sufficient for us. uh, Thank you so much. Thank you so much, sir.
Yeah, thank you so much. Yeah.
Bye, sir.